As I'm sure you know, fire arson is a crime, and it pays for us to know how these crimes are investigated using forensic ideas and forensic tools. Now, we have a problem here when it comes to fire and arson. Uh, the main thing is that when you burn something, you don't have much left. So what kind of clues can you expect to find? Now, we'll see that there are some things that can be done and a lot of evidence that can be collected, even though you might think it's not. There are many difficulties, other specific difficulties dealing with arson. Arson and also bombings, explosive crimes using explosives, they are usually planned beforehand because, nobody wants to stick around when in the middle of a fire. So they're planned beforehand, and their exit route is also planned beforehand. Anything that was planned well beforehand usually is done better and would leave less evidence. So also, it's sure you can pretty much guarantee that they're gone, and they may be in a different state by the time the fire is even started, not let alone investigated. Also, of course, in a fire, your evidence is going to be obliterated, which in fact is often why they commit the arson crimes, to obliterate evidence of other crimes. Also, when firefighters rush in with all their, gushing water all over the place, it's going to obscure evidence too. Also, the thing is, unlike, let's say, a murder, fires and explosives, they do have natural causes, especially fires. Faulty wiring, space heaters that weren't placed right, gas leaks. There are other reasons for fires, and we have to eliminate non-crime origins of arson. So we can't just say, oh yeah, there was a fire. We have to, sometimes a fire was not a crime. So the bottom line is, it takes experience to be able to answer all these questions, to be able to get good evidence. But let's see what we can find out on our own. First of all, we have to know what is burning. What makes a fire? It is technically called oxidation, the reaction of oxygen with a fuel. This is not the technically correct, the chemically correct definition of oxidation, but for our purposes, we will use it. For a fire, it is the reaction of oxygen with a fuel, with the wood of the house, or gasoline, or gasoline, if that's what was burning. Oxidation can be slow or fast, has different rates. Slow oxidation, it means rust and decomposition. When metal rusts, that, believe it or not, is oxygen reacting with, in this case, iron. See, here's the iron and the oxygen, it'll produce this. But very little heat, and it goes very slowly. It can take days or weeks before something rusts. But fast oxidation, that will be, let's say this is methane, that's natural gas. Well, you know what happens when you add oxygen to that and you burn it. That's a very quick reaction, and immediately produces carbon dioxide and water. These are the products, and it produces a lot of heat, and that goes fast. You can burn through several containers of methane in a couple of hours. The chemical definition of oxidation is losing electrons in a chemical reaction. We're not going to use that. We're going to use the definition of combining oxygen with a fuel. So there's the natural gas combined with the oxygen will produce the products carbon dioxide and water and a lot of heat. So why do things burn? That's an interesting question from a chemical standpoint. It's very important. The fact is that it's one of the class of reactions called an exothermic reaction. It releases heat. Exo meaning go out, heat, thermic, heat. Heat comes out of it. There's some reactions that are called endothermic, that heat goes in them, or energy goes into them before they can react. But these are reactions that will produce heat. Here's the first fact that you have to know. When compounds are, let's say, less stable and they fall into a more stable, when they're in a high energy state and they go to a low energy state, they will release energy to get to that state. And of course, vice versa. If you want to get things for lower energy, you got to pump it in. But again, we're not dealing with that. We're dealing with a high energy reactants getting to low energy, naturally going to a lower energy, and the lower energy of the products, and releasing heat in doing so. Now, this is this diagram. We'll see a little bit more about this. Again, we're starting at a high energy. things don't just react with no reason. You got to put in a little bit of what they call activation energy. Once you put in activation energy, then it slides all the way down, releases all the energy difference in the form of heat. Now, it doesn't have to be heat; it could be other things. But for when it comes to fire, we're mainly concerned about the heat that is released. So let's look at natural gas, the CH4, methane, and oxygen. Now, they will not react unless it has activation energy. You start here, and again, let's say you just let gas leak into the air. Air has oxygen, and once you have natural gas in the air, well, nothing really happens. But as soon as you give it a spark, as soon as you give it the activation energy, which again is a form of a spark or a lit flame, you will then cause a reaction. Then you give it that little activation energy, it will react, something that's very fast, to produce the products and release all the energy in the form of heat. That's what's going on here. Now, the heat that's released is the energy difference. Remember, it goes from here, higher energy level, to a lower energy level, and releases the energy that's between them. This energy is heat. So the energy between this and this is heat. If the gap between this energy level and this one is very high, you're going to produce a lot of heat. And the fact is these are high energy molecules, CH4 and O2. CO2 and H2O are low energy molecules. They don't react much. The heat that's produced here, that part of it goes into like warming your hands if you want, or if it's on your gas range which uses natural gas, it heats up the food. So that's where this energy goes into. It goes around the fire, goes outward, and in this case, it will go into your food. Now, some of that heat energy actually goes into producing the activation energy for further reaction. That's why when you burn this, it'll keep burning. You don't have to keep the spark going. You have to keep sparking it, then it'll burn. Spark it again. You don't have to do that. Once it releases the heat that between the higher energy level and the lower energy level, some of that heat goes into making more activation energy, and that will enable more of the reactants to react and produce more heat, which allows more of the reactants to react until your reactants are depleted. Either the methane is gone or the oxygen is gone. Or if you can somehow siphon off all this heat, the heat will be gone. Yeah, you can stop it then, but that's usually not the case. Usually, again, you have a high energy level, give it activation energy level in the form of spark or even a little bit of heat. It'll go down to the low energy level, release a lot of energy. Some of that energy will go into more of the activation energy to allow more of the reactants to react. And this will go on until we have no more of the reactants. There are, just to mention the other kind of chemical reaction, these were exothermic reactions which release heat. There are endothermic reactions which take in heat or take in energy, like photosynthesis. It takes in the energy of the sun and it enables the reactions of the plant so the plant will grow. Also, sometimes heat is not what comes out. We have this energy level difference. Again, you go to high level to low level, energy comes out. It doesn't always come out in the form of heat. It can come out in the form of light or other form, or even some kind of a work. We're not going to be dealing with that. So that's just other aspects of these chemical reactions. So let's look at the heat of combustion, meaning what that is the heat that comes out. That's the difference between the higher energy level and the lower energy level. So different kinds of reactants will produce different energy differences. Let's say you're dealing with something that's really hot.